reaction mechanism. Welcome student. Today we are going to discuss regarding ET reaction mechanism. I am Dr. Devang R. Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Point to discuss in today's lecture is electron transfer, that is oxidation reduction reactions in coordination compounds, that is redox reaction. Type of electron transfer reactions in coordination compound. Another classification of electron transfer reactions. A law of conservation of energy in electron transfer reactions. Type of transition state. And two type of reaction mechanism we need to study for octahedral complexes, and a single electron transfer mechanism is there in our syllabus. So first mechanism of the reaction, outer sphere electron transfer mechanism, with example we need to discuss today, and the second one is the inner sphere mechanism or ligand bridge process, with examples we're going to discuss. Then after factors affecting the rate of direct electron transfer reactions we will discuss today. Let's begin with the electron transfer, that is oxidation reduction reactions in coordination compound. It is well known that in oxidation reduction reactions, that is redox reactions, one or more electrons from a reductant, that is electron rich species, are transferred to oxidant, that is electron poor species. So when I use word reductants, you need to understand that I am talking about electron rich element, whether it is anion, whether it is neutral molecule. And when I referred oxidant, then you need to understand that it is electron poor species. In this process, oxidation state, that is termed as OS, of the reductants goes up while that of the oxidant goes down. Such redox reactions also occur between the two complex ions, one of which act as a reductant and the other act as an oxidant. That means one complex is electron rich, the other complex would be electrodeficient. So redox reaction occur in complexes are called electron transfer, electron exchange reaction, in short ET reaction. Now type of ET reactions in coordination compound. Depending on the mechanism involved in the electron transfer reactions occurring in complex ions, these reactions have been classified under two heads. One is outer sphere electron transfer reaction. The occurrence of these reactions can be explained by outer sphere mechanism, and the other one is inner sphere electron transfer reactions, and these reactions proceed through inner sphere electron exchange mechanism. Now another classification of electron transfer reactions. Another classification of electron transfer reaction in complex ions gives the two type of mechanism. One is the electron transfer reaction in which there is no net chemical change. There is no change in the chemical constituent of the participating reactants. Such reactions are known as electron exchange process, where there is no chemical change take place from reactant to product side. It means it is just an electron exchange process. And the other one, one example of such a reaction if we want to give is this one. Suppose we have hexaamino cobalt complex act as reductant, that is electron rich species, and hexaamino cobalt plus 3 complex ion, that is oxidant electrodeficient species. Now when these two react with each other, we are going to get the same in the product. Only the difference is there, from one cobalt electron exchanging to another. So the one which is marked with this star symbol, that is radioisomer, is converted from +2 oxidation to +3 oxidation state, and the other one which is non-radioactive element, that is cobalt +3, which is +3 in oxidation state, convert into +2. It means that during this process, chemical change won't take place. Only the electron exchanges take place. So this kind of reactions are considered as only electron exchange reaction. These reactions cannot be followed directly but can be followed indirectly by using methods such as labeling of NMR. When we labels with NMR, or labeling or NMR, either we will label it or we will going to take the NMR of the reactants and products. We come to know that yes, electron transfer will take place in this kind of reaction. So electron exchange reaction. Second class in this classification, these are the electron transfer reaction in which there is net chemical change. The example of such reactions is given over here. We have chromium plus 2 hexaaqua complex and chromium plus 3 pentaamino monohalo complex. Now in this reaction you can see that the chromium which is in plus 2 oxidation state convert into plus 3, and this chromium with ammonia is converted into plus 2. But when you going to perform this reaction, you will find net change in the product of the reaction. In this reaction, X are the halogens, maybe thiocyanide, etc. This kind of anions. Another example of this reaction is this one, where hexaaqua chromium plus 2 complex will going to treat with monosulfate, or we can say pentaamino chromium sulfate, and that chromium from plus 2 to convert into plus 3. So one electron transfer from here to here. This is reductant, this is oxidant, and that way we're going to get this product. In this reaction, sulfate 2 minus act as a monodentate ligand. These reactions can be followed by various standard chemical and physical methods. Now, law of conservation of energy in electron transfer reactions, in ET reactions. Let us consider the electron transfer between these two species. One is electro-rich, the other one is electro-deficient. Both are same complex, only oxidation state get changed. In this ion, we will see the reaction. Fe plus 3 hexaaqua plus 3, that is oxidant. This one is the reductant, plus 2 is the reductant, electron rich. So electron from plus 2 enter into plus 3, ferrous to ferric, and that will going to get product 3 and 4. Here the distance between Fe and O, that is 2.05 angstrom, and here in plus 2, that is 2.21 angstrom. Energy state, both this 3 and 4 product is stable state, and here the energy state would be in excited, and due to this excited state the electron exchange taken place from plus 2 to plus 3. So the plus 2 is converted into plus 3 and plus 3 converted into plus 2. In these reactions, ferric hexaaqua complex act as an oxidant and ferrous hexaaqua complex act as a reductant. Electron is transferred from reductant to oxidant. So from reductant to oxidant electron transfer. Product 3 is produced from the oxidant and product 4 is produced from the reductant. The equilibrium Fe oxygen distance is in the first one, that is the oxidant, that is 2.05 angstrom, and that would be in the reductant 2.21 angstrom. Now, since according to the Frank-Codin principle, the internuclear distance in a molecule remains unchanged during electron transfer reaction. This is Frank-Codin principle. That means the velocity of electron during the process when ET reaction take place, velocity of reaction is higher than that of the nucleus. So internuclear distance in a molecule remain unchanged during the electron transfer reaction mechanism. These two values should not get changed. The Fe oxygen distance in product 3 should be same as that of its stable or ground state or lower energy state. 2. Fe oxygen distance in 3 should be equal to 2.21 angstrom. But actually Fe oxygen distance in product 3 has been found to be shorter than 2.21 angstrom practically. This indicates that product 3 would be in the higher energy or excited state. This state, as for example, 3 would come to the lower energy or ground state by losing the excess energy to the system and will thus adjust its Fe oxygen distance to 2.21 angstrom. And that way the energy of the system conserved. In the similar way, fourth product would be in the higher energy or excited state and would come to the ground state by adjusting its Fe distance to 2.05 angstrom. And after the product 3 and 4 attain the stable state, these are in no way different from the reacting complex, that is 1 and 2. So that energy is going to be consumed during the process. Hence they can again participate in electron transfer reaction and can again liberate energy. Thus, the electron transfer reaction between complex ions having the same central metal ion in aqueous solution would lead to the constant generation of energy. And you can use this in energy generation without consuming the chemical compound. This is against the law of conservation of energy. This law is not violated if the metal ligand distance in all the 4 complex ions is made equal to each other prior to the electron transfer between them. Now, type of transition state. 2 types of transition state or intermediates are generally formed during the electron transfer reaction. First one is outer sphere transition state. An outer sphere transition state is that in which the inner coordination sphere of the 2 reacting complex ions involved in the electron transfer reaction remains intact. That means there is no change in the coordinating sphere of the reacting species. While the inner sphere electron transition state is such transition state in an electron transfer reaction is that in which the coordinated ligand of one reacting complex ion form a bridge with the other reacting complex. That means the coordinating sphere of the transition state get little change than the reacting species. Now, mechanism of one electron transfer reaction, and first there are 2 types of one electron transfer mechanism, inner sphere and outer sphere. We will going to discuss outer sphere reaction mechanism first. The electron transfer reactions whose occurrence can be explained on the basis of outer sphere mechanism are called outer sphere electron transfer reactions. Main characteristic of outer sphere mechanisms are: number 1, in outer sphere mechanism, direct transfer of an electron from the reductant to oxidant occurs. Hence, electron transfer reactions proceeding through outer sphere mechanism are also called direct electron transfer reactions. So, another name of this outer sphere mechanism is direct electron transfer mechanism. That is also known as outer sphere mechanism. So if examiner can ask you direct electron transfer mechanism, you need to explain outer sphere mechanism only. Second point, electron transfer reactions take place between 2 metal ions if the metal ions are inert and have saturated or coordination cell. Coordination, correction, typological mistake. Saturated coordination cells, or one of the metal ions is inert and its coordination cell is saturated. In the latter case, none of the coordinated compounds would be a bridging ligand. Here there is no bridging ligand and both the metals should be inert. Their coordination cell should be equal, saturated, and there is no change chemically during the process. That is outer sphere mechanism. Third point, the rate of transfer of electron depends on the polarizing power of the metal ion. More the polarizing power, more rate of electron transfer would be. The rate of transfer of electron between the two metal ions of the same metal is fast if metal ligand bond distance in the reductant and oxidants are very nearly equal to each other, nearly equal to each other, the bond distance should differ very slightly from each other. And if the electrons are able to reach the surface of the complex either through unsaturation or through conjugation, if the electron to be transferred from the reductants to oxidant is present in instead of it is in is present in T2G orbital of the metal ions acting as a reductant. And D, if the coordinated ligand present in the reductant and oxidants are pi acceptor. So these are the 1, 2, 3, 4 points that the rate of transfer of electron between two metal ions of the same metal is fast, and the reason is this 4 point. Fifth one, leaving aside the electron to be transferred, the central metal ion present in reductant and oxidant have the same electron spin. And last one, if the reductant and oxidant both are inert and their inner coordination cells are saturated. So these are the conditions for the outer sphere electron mechanism. Fifth condition, the rate of the transfer of an electron from the reductant to oxidant is slow if electron to be transferred is present into EG orbital. In the central metal ion, we have studied the MO diagram. If the electron present into EG, then the transfer rate of the electron would be slower. Leaving aside the electron that are to be transferred, the electron transfer reaction between two metal ions present in the reductant and oxidant would be easy if both the metal ions have the same electron spin. We know that in hexaamino cobalt plus 2 ion, this complex ion is a high spin, and hexaamino cobalt plus 3 complex ion is a low spin complex. Thus, these ions do not have the same electron spin. On the other hand, both the complex ion, namely hexaamino ferrous plus 2 and hexaaqua-ferrous plus 2 and hexaaqua-ferric plus 3, both are high spin complex. Consequently, the transfer of electron from this hexaaqua-ferrous to ferric would be easier compared to hexaamino cobalt plus 2 to hexaamino cobalt plus 3 would be more difficult. Now, 7 condition in the outer sphere mechanism. The larger is the difference in the oxidation state of the two reactants, larger will be the adjustment needed in the metal ligand bond length, thus calling for the higher activation energy, and hence slower would be the redox reaction. So if we have a larger difference in the oxidation state of two metals participating in reactants, instead of +1 difference, if there is +2 or even +3 or more difference in the oxidation state, then we need more adjustment in the bond length between metal and ligand, and as a result a lot of energy is required for activation. To reach to activation energy, the reaction is going to be slower one. 8 point, most of the electron exchange reactions in which both reacting complex ion as one complex ion act as an oxidant and the other complex ion act as a reductants are inert towards substitution, have very high second order rate constant. The rate law should be first order in each of the two reacting spaces, that rate is equal to K by concentration of oxidant into concentration of reductant. 9th point, the activated complex should contain intact coordination cell for both the metal ion. There is no change in the outer sphere. And 10th, According to Frank-Curtin principle, there can be no appreciable change of atomic arrangement during the time of electron transfer. 11 point. If the renting complex ions are inert, a close approach of the metal atom is not possible, and therefore the electron transfer must occur through tunneling or outer sphere mechanism. This is fine condition for the outer sphere mechanism, and that is why it is known as tunneling mechanism as well. Hence, the redox reaction occurring through outer sphere mechanism are also called electron tunneling reactions or direct electron transfer. Now you have three names for outer sphere mechanism. One is electron tunneling reaction with mechanism, or direct electron transfer reaction with mechanism, or outer sphere electron mechanism. So three ways the examiner can ask you. Please keep it in mind. 12 point. The outer sphere electron transfer reactions are more rapid when the reacting complex ions contains the ligand like cyanide, O, phenanthroline, etc. Then when they contain the ligand like ammonia or aqua, etc. 13 point. Outer sphere exchange reaction between the complex having different central metal ions with different oxidation states. Suppose here we have osmium 2 with molybdenum 5. So plus 2 to plus 5. Major difference is there in these two complex ions are usually faster than the outer sphere exchange between the complex of the same metal with different oxidation state. We have the example for that. Here the oxidation state plus 2 plus 5, so converted into plus 3 plus 4, and it's a very rapid fast reaction. This is reductant, this is oxidant, and these are the product. For such reactions, when excited state of the products are converted into ground state, the decrease in the energy can appear as the free energy of the reaction, that is delta G0 must be negative, otherwise the reaction would not take place. Here that delta G would be negative, and therefore when you put these two complex into aqueous solution, the electron transfer take place on its own. It is automatic reaction. This means that for such reactions, the structure of the transition state is more like that of the reactants, and consequently the activation energy is decreased and the rate get increased. Now 14th, in the outer sphere mechanism, no binuclear intermediate is formed. There is no kind of bridging ligand between two center. In outer sphere redox reactions, the electron effectively hops from one species to other, and the ligand acts as an electron conduction medium. So there is no any kind of linkage between the two center during the reaction. Here you can see that outer sphere mechanism. We have these two reactants, and when these two reactants associate, that means we'll get into the same kind of solvent. Bridge formation won't take place over here. You can see there is no bridge formation. Direct one center to another electron transfer take place, and then after the successor complex is going to be diffused apart, and we're going to get different product where only the oxidation state of the metal center metal ion get changed. That is outer sphere electron reaction mechanism, electron transfer reaction mechanism. Next example of the electron transfer reaction mechanism proceeding through outer sphere mechanism. In order to understand the outer sphere mechanism, let us consider the transfer in this reaction. We have hexaamino cobalt plus 2 and hexaamino cobalt plus 3. So this one is going to be our reductant, this one is going to be our oxidant, and the transfer of electron take place from reductant to oxidant. So reductant turns into higher oxidation state, oxidant turns into lower oxidation state, and we're going to get this products. The rate of this reaction, which is actually not a chemical reaction, can be studied by using labeled cobalt atom, that is star cobalt, in the complexation. The details E above reactions are given in this figure. This is the detailed figure. We have reductant, which is high spin complex, and oxidant, that is inert low spin complex. So from high spin complex, active complex electron transferred to low spin complex. Oxidations change from +2 to +3 and from +3 to +2. Here the cobalt is in D7 configuration, that here in the cobalt is D6 configuration. Here T2G5 Eg2, N is equal to 3, where N is equal to 0, T2G6 Eg0. There is no electron in Eg. Now when the reaction takes place between these two, this one converted into T2G5 Eg1 and this one T2G6 Eg1. So one electron from this Eg enter into this Eg. And the bond length between cobalt and nitrogen is concerned in the case. Here the length is large, that is 2.11 angstrom. Here as the oxidation state increase, bond length get decreased 1.96 angstrom. Here also the length get decreased 1.76 angstrom, and here 2.31 angstrom. And when this lost the energy, they will try to find out this one and maintain the law of conservation of energy. This is electron transfer between hexaamino cobalt +2 and hexaamino cobalt +3 complex ion, and that way we have indicated with the star. Since the oxidant, that is the cobalt +3 hexaamino cobalt +3 complex ion, is an inert complex ion, and cobalt ion has saturated inner coordination cell, the exchange of ammonia ligand between the two reacting complexes is extremely slow. Since the lone pair electron on the nitrogen atom of all the ammonia ligand is consumed in forming the nitrogen to cobalt coordination bond, the atom has no other lone pair remain on the nitrogen of ammonia and can form a bridge between these two cobalt atom, and therefore inner sphere mechanism between these two complex is not possible. Consequently, the electron transfer home the reductant to oxidant must occur through outer sphere mechanism, in which the inner coordinated cell of the reductant and oxidant remain intact in the transition state as well. The coordination sphere of both the reactants and products remain undistorted. The transfer of an electron from reductant to oxidant make a change in oxidation state of the metal ions only. The increase in oxidation state of metal from +2 to +3 result in the shortening of the metal ligand bond length, which we have already seen that from 2.11 angstrom it converted into 1.76 angstrom. As the oxidation state increase, bond length get decreased. In the product 3 is produced from 1 and product 4 is produced from 2. The observed rate of the electron transfer in the above reaction is slow, and this may be due to the reason. First reason is since cobalt nitrogen bond length in the reacting complex ion are appreciably different from each other, considerable amount of the energy of activation is needed to excite the two reacting ions to have identical cobalt nitrogen bond length, so that electron transfer between the reactant complex ions may occur. Second reason, the electron to be transferred from the reductant to oxidant in the Eg orbital of T2G5 Eg2 configuration of cobalt +2 in the reductant. Now since dz square and dx square minus y square orbitals of Eg set along with s and p orbital of the metal are already engaged in forming metal ligand sigma bonding, which we have already seen in the MO diagram in a previous unit, the transfer of Eg electron from T2G5 Eg2 configuration of cobalt +2 labeled ion would require more energy. And third reason, the spin state of the cobalt +2 and cobalt +3 ions present in the reacting complex ions are different. One is high spin, other is low spin. Cobalt +2 present into hexaamino cobalt +2 D7, that is T2G5 Eg2, that is a high spin complex, and cobalt plus 3 present into hexamino cobalt plus 3 complex ion. D6 configuration, 6 is superscript, T2G6 Eg0, that is a low spin. So from high spin to low spin, this transfer is little difficult, and that is why it is slow one. Another example, some example that you need to do it for yourself, that is for self study. This different example I am going to put it over here, one after the other. Is here cyanide ligands are there, here diphenyl ligands are there, here we have biphenyl ligands, cyanide with manganese, aqua ligands, chloride ligands where electron transfer, ethylene, bis ethylene diamine, bis ethylene diamine, oxalate, oxides. So these are the examples that you need to follow, and out of those examples, these points we can draw out. The complex in tris biphenyl ferrous plus 2 complex ion and tris biphenyl ferric plus 3 react very fast, since metal ligand bond length in these two species differ very slightly. There is no major difference in the metal ligand bond length. On the other hand, the complex in hexaquaferrous and hexaquaferric reacts very slowly, since there exists a considerable difference between the Fe-oxygen bond length in two species. The difference calls for a lot of adjustment in Fe-oxygen bond length in the exchange species. A large activation energy is required compared to the above example of tris biphenyl ferrous to ferric pair. As a result, the ferric plus 2 to ferrous plus 2 to oxygen bond length in hexaquaferrous is 2.21 angstrom, while in ferric or 2 oxygen bond length in hexaquaferric plus 3 is 2.05 angstrom. And as a big difference between these two bond length, more activation energy is required, so electron transfer is slower in this one, while electron transfer is faster in this one. Rate of the electron transfer for reaction 1, 2, 4 is more than 10 raised to 6, while in this value for reaction 3 is more about 4. For the reaction, this value is about 10 raised to minus 4. Different in metal ligand bond length for reactions 1, 2 and 4 is very small. This is this numbering for 1, 2, 4 is for the example which I have put it for your self study. Redox reaction 7 has been studied by Shepard and Weil. In this reaction, both the reacting anions are inert towards substitution. Data shows that the transfer of electron from manganese oxide from +6 to +7 oxidation state take place rapidly, and tunneling mechanism seems to be the most probable mechanism in this species. This is inner sphere electron transfer mechanism. Now how it differ from the outer sphere? You can see that two complexes are there, octahedral complexes. Well, they come together when you add into aqueous solution, so precursors complex take place. Now one of the ligand which act as bridging ligand and attach with both the metal centers simultaneously, and the electron transfer take place through that bridge ligand. In the above case, there is a direct transfer of electron from one center to other. Here the electron transfer take place through or via this bridging ligand, and then the supersuccessor complex diffuse apart. Those bridging ligand which is now with this complex turn to this complex. So even the bridge can get changed from one complex to other. So chemical change is observed in this inner sphere mechanism as well compared to the outer sphere. Let's study inner sphere mechanism or ligand bridged process. Two ways the examiner can ask you. On the basis of the extensive investigation made by Taube, he suggested that the main characteristic of electron transfer in reactions occurring is through inner sphere mechanism, or one of the reacting complex ions should be inert and the other ion should be labile. Two species, when one is inert, other is labile, then the bridging ligand will going to attach with the two center and electron transfer take place. The inert complex ion should have a coordinating ligand which is capable of forming bridge between the two reacting complex ions, reductants and the oxidant during the formation of intermediate, which is called the bridged ligand or bridged transition state or ligand bridged intermediate. The rate of electron transfer in the reaction increases if the bridging ligand has unsaturation or extended conjugation in its structure and with the increase of nucleophilic character of the bridging ligand. In the electron transfer reaction occurring through the inner sphere mechanism, an atom or a group is transferred from one reacting complex ion to other reacting complex ion to form an atom or a group bridged intermediate, and the electron is transferred from reductant to oxidant in this bridge intermediate. Now the intermediate break up to give the product. The transfer or non-transfer of the bridging atom or a group depends on the relative stability of the product obtained by the breaking of the bridge intermediate, but most of the time the bridging atom is transferred from one complex to another. Example is iridium hexachloro -2 complex ion treating with hexaaqua chromium +2 complex ion. This one is your oxidant, that is electrodeficient. This one is your reductant, that is electron rich, and from chromium electron enter into iridium. So from plus oxidation, 4 oxidation state is converted into +3 and +2 is converted into +3. The product obtained in the above condition so that no transfer of bridging chloride atom has occurred, but electron has transferred from reductant to oxidant. So here there is bridging ligand is not get changed from reactant to product side. So this is the example for that one. Chlorine bridged intermediate is formed in the reaction has this structure pentachloroiridium, and this chlorine is going to attach with both iridium and chromium both together, hexaaqua. So this is your bridging intermediate, bridged intermediate of these two complex. So these two complex convert attached by chlorine and then give the product after the transfer of electron through chloride. This intermediate on break to give two type of product. So here you can see that there is two type of product. On hydrolysis the intermediate will going to give either these two product which are more stable or these two product which are less stable. Since the product of the reaction, that is 1 and 2, are more stable than the product 3 and 4, chloride bridge intermediate is formed, and this break to give the product 1 and 2 and not 3 and 4, because this 1 and 2 are more stable, so it gives 1 and 2. Electron transfer in the reaction proceeding through inner sphere mechanism are faster than those in the similar which proceed through the outer sphere mechanism, because there is a bridge, so electron transfer is becoming little bit easier. You can see that this is reductant, it is labile, this is oxidant, that is inert. So from reductant to oxidant the electron may get transferred, and here this X is going to be the bridging ligand, and we're going to get this two product, where you can see that here there is no bridging ligand, now here there is a bridging ligand. So here bridging ligand get transferred from one complex to another. This reaction proceeds through these steps: formation of bridge intermediate and electron transfer. The ligand X, which is present in the inert oxidant, get dissociated from the oxidants and is transferred to the reductants to form an bridged intermediate 1, in which X minus act as a bridging ligand between the reductant and the oxidant. Within the bridging intermediate 1 thus formed, an electron is transferred from reductant to oxidant. So from reductant to oxidant, through this bridging ligand, electron get transferred. You can see the mechanism over here. This is the mechanism. Here you have reductant, this is a labile, this one is inert. Now they, when attached by this bridging ligand, so electron transfer from chromium to cobalt, and after the transfer, the chromium, which is +2, now converted into +3, and cobalt, which is +3, now converted into +2. And then when the bridge intermediate breaks, the bridging ligand will go with the chromium, not with cobalt. A decomposition of the bridged intermediate into products, hydrolysis, the bridged intermediate 2 formed as above gets decomposed. This will undergo hydrolysis to give the final product. So the hydrolysis will going to give us final product, but in the final product, the bridging ligand instead of cobalt now comes to chromium. So we can say that bridging ligand is with chromium. Step A is a slow step, and hence it is a rate determining step. Thus, the rate of electron transfer in the reaction can be explained as rate constant K into concentration of the hexaquachromium +2, that is reactant, and oxidant, concentration of oxidant. So we can write as concentration of reductant and concentration of oxidant. Reaction 1 gives above shows that the rate of the electron transfer in the reaction change with the change of the halide ion present in the oxidant. The capabilities of halogen ion to form chromium X cobalt bridge in the transition state decrease, as if we can change the halogen with iodine, it has we can say if we're going to put iodine over here, transfer become more lower slowly, bromine even slowly, it was little faster, and chloride little more faster. With a decrease in the capabilities, the rate of the electron transfer in the reaction also decrease in the same order. This is the example for your self study. Here we have these two kind of complex ion, and you need to take this one as a bridging ligand and do it yourself. Now this is comparison between inner sphere and outer sphere. In inner sphere you have bridging ligand. Here in outer sphere there is no bridge formation. Direct metal to other metal electron transfer is taken place. So that is the difference between inner sphere and outer sphere mechanism. Factors affecting the rate of direct electron transfer mechanism. Electrostatic repulsion between ions of like charges. This contributes to the activation energy. Because of the electrostatic repulsion, the energy activation also increases. The increase in activation energy tends to decrease in the rate of electron exchange. Second point is identity and concentration of the cations present in the solution. In several cases, the rate constant for the electron transfer reaction has been found to depend on the identity and the concentration of the cation present into the solution. Generally, an increase in the concentration of the cations increase the rate, but certain cations are particularly more effective. The general effect can be attributed to the formation of ion pairs, which then decrease the electrostatic contribution to the activation energy. Third is the conductivity of the ligand. Complex ions have ligand for higher conductivity exchange. Their electrons are more rapidly than the complex having ligand of lower conductivity. For example, since phenyl and biphenyl ligands have higher conductivity than ammonia and ethylene diamine, we can see that these two complex ion exchange electron transfer more rapidly compared to these two metal complex ions. Now reorganization of the energy. The bond length in manganese oxide differs the activated complex for exchange between this most involved a stretched metal oxygen bond in manganese oxide. Slow reactions are expected when the oxidant and reductant have greater difference between the bond length, geometries, or solvation cell. For octahedral complexes, bond lengths are changed more drastically when Eg electrons are involved in the transfer as compared to the T2G electron involved in the d orbital. Now fifth is the free energy change in the reaction. Free energy change of the reaction also affect the rates of outer sphere reactions. The electron exchange reaction will be fast if the free energy change for the overall reaction is negative. with the increase of the free energy change, the exchange of electron is lower down. With this, thank you very much for paying attention to this lecture.